So type 2 plus 1 0 makes it type 3. R1, R2, RP, so H of comp 3s, we are looking at Kp plus Ki over s, this was your type 2, and we need one more 0, 1 plus s over, I will call it omega z2. Okay, type 3. So this is nothing but your type 2. So you have two zeros now. First 0 is coming from your type 2, second 0 is we need to add. So how can I add this 0? What changes I need to make to have this additional 0 in the same circuit? Yes, that's it. I'll call it CD, let's say. Why I'm calling CD, I'll tell later, but for now just call it CD. Okay. So let's see how this transfer function gets modified. So can I write this Kp plus Ki over S equal to Ki over S 1 plus Kp over, okay, Ki over S into 1 plus S over omega z1, where omega z1 is nothing but Ki over Kp. Okay. So H of comp S, comp 3s becomes Ki over S, Ki 1 plus S over omega z1 into 1 plus S over omega z2 over S. Okay, so you have one integrator and two zeros. First 0 will cancel your integrator, second 0 will give you the phase boost which you are getting from ESR in the cap. So now that ESR is replaced with this omega z2, so your ripple will not change. So you can still get a smaller ripple and compensate your circuit. So now let's multiply this. So what you get, 1 plus S over omega z1 plus S over omega z2 plus S square over omega z1 omega z2, and I can write this Ki over S 1 plus S Okay. So I just moved this term here, nothing else, and I have taken 1 over omega z1 common. So what is this? Ki over omega z1. Okay, I can write like this. So what is this? Proportional integral derivative. That is why we call PID type 3 as PID. And if you know the Kp, so this becomes your, I will call it Kp dash, because Kp we already defined here. Now because of that second 0, your proportional gain will be affected. So if you make omega z1 and this omega z1 and omega z2, let us say, separated out, then this factor will be small, then your Kp will not get affected in that case. So let us say omega z1 is 1/10 of omega z2. Okay, so it will be 1.1, no difference, but we are considering omega z2 as at resonance the other one half, so you will get a 0.5 factor here. Okay, so your Kp which you may require in the, let us say, Pi 4 or so, here it will become 1.5 times of that. Okay. And this effect we already consider when we calculate the values, because when we calculate the gain, we consider the effect of second 0. Okay, so that will be already taken care in that. So integral and derivative. So derivative is the extra component we are getting. So I mean, so some people define it as Ki and Kd, the coefficients. Okay, so Ki over S I can call it, and Kd into S, and that is what they do, like you choose appropriate Kp, Ki, Kd and compensate your. So if I want to have the same compensator type 2, I can do this also. Huh? I can have Kp dash, or let me draw it as gain. Kp dash, Ki, Kd, integrator, differentiator, sorry, not here, wrong position, integrator, so if I call it Vi, or this was your V out there and this was your VCTRL. So you will get the same thing out of this. So what you need one integrator, one differentiator and one gain element, and that all you know how to design. The only thing is this will require 3 op amps. The same thing you can achieve with a single op amp there. Okay. So but here you can independently control all the 3 parameters. In the previous case, if you disturb one, it may disturb the other also, like your Kp and Ki are coupled together, correct? And then your proportional gain and integral gain both, if you look at the resistor here, which is changing the second 0, the R1 will change your integral gain also. So, Ki is coupled with everywhere, and that is why you are getting Ki in all the 3 terms here. If you look here, Ki, Ki, Ki. Okay. So, you cannot control independently, here you can control independently, and that is what people do when they say they are design a PID compensator. This is used in motor drive also. So, they control all the 3 parameters independently, but ultimately what they are doing nothing but they are doing the same thing. They are just positioning the 0 and adjusting the gain, that is it. So, from here if you know Kp, Ki, Kd, you can back calculate the 0 locations and your gain, and we understand the behavior of the system in terms of your Bode plot better compared to, if I tell you Kp, Ki, Kd, you choose this, you cannot just tell that whether it is stable or not, but somebody tells me my 0 is here, my gain is this, you can directly tell whether it is stable or not. Okay. So, that is why we always analyze in terms of 0 rather than analyzing in separately Kp, Ki, Kd. Okay. But both are correlated and you can design it either way. The only thing is that you can do with a single op amp, here you will require 3 different op amps. Okay. Or you can couple you can do it with the 2 op amp also, you can couple Kp and Ki, that will make Pi. So, Pi plus derivative with the 2 op amp you can also do. So, if I want to write Kp in terms of from here, what will that be? Rp over R1? Correct. So, because Ki is 1 over R1 Ci, okay, and omega Z1 is RPCI. So, CI cancels out. So, Rp over, and if you intuitively want to look at, so after first 0 appears, this capacitor will be considered as shorted. Okay. And what would happen to this? This cap is at a higher frequency. So, in mid band what you are seeing, this minus Rp over R1. So, it is simply inverting amplifier. Okay. And the same can be simplified and we can break into 3 different components: proportional, integral and derivative, and that is why it is called PID or proportional, integral and derivative compensator. And you can implement that by having all 3 coefficients separately, by having a amplifier which will give you the proportional gain, then integrator which will give you the Ki coefficient, and Kd you can, so derivative. So, basically the gain of integrator and differentiator will be nothing but Ki and Kd, the coefficients, and you add all the 3 and you can independently tune all the 3, but ultimately what we are doing here, by changing Ki, Kd or Kp, you are simply changing gain and location of your 0, so that you can get enough phase margin to make it stable. So, I will just copy this. If I want to draw the phase and magnitude response of this HCOM 3S, so what will you have? So, this is your omega and this is your dB gain. So, what is the first thing you have here? So you have an integrator, okay. So the first portion of this is nothing but will look like a type 2. So in the type 2 you are adding one more 0. So the first 0 appears here. Then you have second 0. Okay, and you don't have any pole here, so it will keep going unless you have a pole that will flatten it out. Okay, so we'll add that pole later, but for now simplicity we will consider only 2 zeros and one integrator. Now if I want so what about the phase? How will it start?
Start from minus 90.
Minus 90 or it's inverting, huh?
Minus 90 plus 180. So 90 degrees. Full edge of 90 degrees. Because we have a negative sign.
Okay.
180 degree minus 90 degrees. Come on.
So if you are going in one direction, usually what you do, you start with minus 180, okay, and you are going towards minus 360. Okay, when you have a two poles, it will give you minus. Okay, or if you are starting from positive, then you go towards 0 side. So you can look either way. You can start with 180 or minus 180, but the only thing, what is the at the end my total phase shift you are looking at, whether 360 or 0, it's same actually. So since we know that all the poles are going to add negative, so we simply start with minus 180. Okay, or what you can do, in the HCOM 3, instead of plotting angle of HCOM 3, you can plot angle of HCOM 3 plus 180, so that you can start with minus 90. Okay, so that offset will basically shift your phase shift. So minus 180 and then you have a one integrator, so it should be minus 180 plus, not plus 90 but minus of 180 plus 90, so minus 270. Minus 270. Then you have a 0. So at omega z1 what should be the phase?
Minus 3.
Minus 180
Plus
45.
plus 45. Okay. How much is this? Minus 225. Then second 0. So the omega z1 and omega z2 are
Like phase shift
pretty close, huh? So phase, where the, in which direction phase should go?
Actually, the phase should will increase.
So you have a 1 integrator and 2 0. So what is the maximum phase shift at the end you will get? Plus 90. So we should take it in the other direction actually. Let me just start from a lower, so that minus 270 and I will do this way. Okay. Minus 225 and what will happen after that? So, let us say omega z1 and omega z2, if they are far away, then it will go towards settle at minus 180. So, it should go towards minus 180, okay. But due to the second 0, so it depends how much separation you have between omega z1 and omega z2. So, it may settle and flattens out at minus 180, but if your second 0 hits before that, then it will keep rising towards plus 90. Okay. So, this shape could be anything. I mean, it may do this and then rise. Okay. So, it depends where omega z1 and omega z2 are located, but usually this is what will happen because we know omega z1 and omega z2 are not far away. At least there should be 1 decade of separation in order to make sure you get the phase saturated at minus 180. So, let me just move this here. So, which means, so where should I have my omega UGB? So, your omega UGB should be between omega Z2 and not Z2 Z1. After Z2, you cannot move your omega Z2 out of UGB, you won't get any phase margin. So, you want to maximize the phase. So, the phase margin is coming only because of omega Z2, because omega Z1 is what doing? It is only cancelling the integrator. So, the phase is neutralized here. So, plus 90 minus 90 gone 0. Now, the phase boosting you are getting only because of omega Z2. So, how far it is from, or basically I would say how early you have from UGB omega Z2, that will decide your phase margin, tan inverse omega UGB over omega Z2. Okay. So, if you have a 1 decade of difference, then you will get almost 90-degree phase boost, and that will define your phase margin. Okay. So, your omega UGB usually is between omega, let me write here, omega UGB is greater than omega Z2. Okay. And your omega naught LC, where it should be?
Around omega Z2.
So, it can have, so it could be near omega Z2, okay. You can have after that only if your Q is very low, but if your Q is very high, then you should have omega Z2 at omega naught, because you do not want that phase to cross to 0.